The second topic of this module is regression with non-stationary variables. We will go through the concept of stationarity and what is the difference between stationary and non-stationary variables. We'll introduce the concept and the consequences of spurious regressions. After that, we'll introduce a couple of tools like unit test for non-stationarity and code integration test. Finally, we will have a discussion about the strategies to deal with a different type of non-stationary variables. First of all, what is a stationary variable? If a time series is stationary, it has to meet all of these three conditions as given on this slide. The first one is the mean is constant at different point of time, so the mean shouldn't change. Second, the variance should be constant across time as well. And finally, the covariance depends on S, not T. S is time interval. So if the interval is the same, doesn't matter where you look, at which time point you look at, the covariance should be the same. So those are rather strict conditions to meet in order for a time series to be stationary. Moreover, if a time series is not stationary and it doesn't have this constant mean, we will describe it as not having the property of mean reversion. In practice, mean reversion is very important attributes to have. That basically means it doesn't matter how far away this time series wander away from its mean, eventually it will come back. So we have some sort of a benchmark or even expectation about where the value should be, what the value should be. So it's a nice property to have. Stationary series obviously have the property of mean reversion. Non-stationary ones doesn't have. On this slide, I showed several stationary and non-stationary variables. So left-hand side, the first one, chart A, that's the real gross domestic product, GDP, apparently is not stationary. Why is that? Because if you cut the chart into a couple of sub-periods, for example, by 5 years, you may notice that the means are not the same across time. Apparently, the mean has been increasing. So it's obviously not a stationary time series. Chart B, this is the changes in GDP. So that's 1 year change in GDP, first difference basically. And you may notice in comparison, this one appears to be more stable. So it's likely to be stationary, even although at the end, there's some substantial changes over there. But overall, it looks like they have a mean around 100 something over there. So the first difference of GDP is more stationary compared with the original data, the level data. Similarly, chart C is the inflation rate. And you may notice that the means are not the same in different subperiod. At the beginning, the means obviously, there's two parts that those are higher and those are lower towards the end of this time series. But after we take the first difference, that's the 1 year's change of inflation rate. So changes in inflation rate is plotted in chart D. And you may notice that it roughly is fluctuating around the 0 line. So it looks like that is probably is stationary. On this slide, I give you two more time series. One is the federal funds rate. Another one is just a 3 years bond rate. Right-hand side, similarly, I calculated the first difference and plot them against time. Once again, the level data, the original variables like the federal funds rate and the 3 years bond rate, they don't look like stationary to us, because the means apparently changed over time. On the other hand, the first difference, for example, for the changes in the federal funds rate, fluctuates around 0, and this one looks like fluctuates around 0 as well. So they are more stationary. We can calculate those discrete statistics to verify our observation. So in this table, I divide the sample period simply just in half. So left-hand side, that's the first half. The right-hand side, that's the second half. And then I calculated the mean for each subperiod and for both set of data as well. So the first set of data or first set of variables are level variables. They are the original variables. The second set contains the first difference of those four variables. So if you compare the means for levels, you may notice the difference is quite large. So for example, this one is more than almost double of the means in the first period. Inflation rate, that's a similar story. So it's half of what we had in the first period. On the other hand, if you compare the difference between those periods among those changes, the changes are quite small, particularly for the last two ones. So for example, the changes in the federal funds rate, the average value, the means in those two subperiods are virtually the same. The same pattern is true for changes in bond rate as well. And this type of a pattern usually holds in practice. In other words, if you take first difference of a non-stationary variables, usually it will become stationary. So first difference is the way to transform non-stationary variables into stationary ones. This is one of the techniques we're going to introduce later. We now need to introduce several jargons or terms in time series analysis. The first one is stochastic or random process. That's basically another way to say we have an econometric model. It's an equation. This is how the value of y is generated, and we call it stochastic or random process. And a sample of observed yt value or a particular value of yt is called a realization of this stochastic process. In other words, that's just a specific value of this equation. For example, if we have an AR1 model, as I mentioned before, so this equation is a stochastic process, a random process. That's the equation for us to generate the value of y. And if y1 equals 5, then this 5 is a particular realization of this process. In addition, we require this Vt, the errors of this equation to be independent with a zero mean and a constant variance sigma v square. And they may be normally distributed. That's not a very strict requirement in terms of normal distribution. Because when sample size is large enough, usually we can reliably assume that it's normally distributed. We call errors in this equation as shocks or innovations. That basically means, okay, we have some sort of a stable relationship over there and can specify by this equation. However, this random error is something that we do not know very well. Sometimes it can come in really big. It's called a shock, and it can change the direction of the trend significantly. We'll come back to that point later. The most important attributes of this equation is in this AR1 process is rho, this coefficient of yt minus 1, is quite important for us to decide whether the time series is stationary or not. So if the absolute value of rho is less than 1, this process is stationary or stable. Otherwise, it's not stationary, it can be explosive. I now have several examples of both stationary and non-stationary variables as examples to show the difference among them. All of those time series are generated in my computer, so those are artificially generated by using the equation showing on the slide. So for example, the first one is a stationary variable with a zero mean. So that's generated by using this formula, yt equals 0.7 times yt minus 1 plus vt. So if you calculate the expected value of yt, that's 0. And you may notice that the pattern of the stationary variable is pretty random because primarily determined by the error term vt. And it is all the values are distributed around the zero line. That's the mean. The second one is generated with this equation, yt equals 1 plus 0.7 times yt minus 1 plus an error term. So that's stationary because the coefficient over there is 0.7, it's less than 1. But it has a non-zero mean that is determined by the 1 over there, okay? And I can calculate the mean of this yt is equals to 3.33, okay? So alpha here is just the value of value over there is 1. That's the intercept term in this equation. And because it's time series, those information keep fading into future observations. This is why the mean is 3.33 instead of 1 over there. Okay, so you may notice that, okay, the pattern is quite similar compared with the first one, other than the fact that the values are surrounding the mean that is not 0, so somewhere over there around 7 or around 3. The next one is stationary but around a linear trend. So the linear trend can be derived from this equation, and you have a constant over there. You also have a linear trend, so t is a time index. In this example, it goes from 0 all the way to 500, so 500 time period. And because rho here equals 0.7 is a stationary time series, but it does have a trend, and the mean is not 0, obviously. So along this trend line, if we do not look at the trend line, it's an upward trend, the distribution of those observations are quite randomly surrounding this linear trend. So it's stationary, although it does have a constant increasing trend. So that's the third stationary variable that we can generate from this process. And if now we change the rho or the coefficient of yt minus 1 to be a value that is greater than or equal to 1, we are not going to have a stationary variable. Okay, you may notice the pattern change significantly compared with the previous one. And here we just change the coefficient from 0.7 to 1. So yt equals yt minus 1 plus vt. It is not stationary, and we call it random walk because it's just like some person randomly walking and there's aimless. And the summation of those shocks is called a stochastic trend. And we can derive the mean and standard deviation from this process. Although the mean is still constant, the mean is the initial value of y. The variance is not a constant because when t change, the variance of yt will change as well. That's an indication of non-stationarity. The next one is still non-stationary because the coefficient of yt minus 1 is still 1, but we add a constant term to this random process, so that's 0.1. Even small, you may notice that the pattern changed significantly. It's because this 0.1 just keeps fitting into the system step by step, and eventually it gets really large. So we have a trend here. The mean is not constant. You may notice it change over time. So t times alpha. Alpha here is just 0.1. And the variance, again, is not constant. It changes over time. So this clearly is not a non-stationary time series. The last one has not just a constant term, but also a trend in the stochastic process. So if we use this equation to generate the time series, you will have a clear pattern over there. That's a very strong trend, simply because both 0.1 and 0.01 are positive. So over the time, this kind of impact will accumulate. It gives you a very strong upward trend, and we can derive the mean and the standard deviation of the of yt, and obviously similar to the previous one, both of them are not constant across time. In other words, they change when t change.